So in this entire playlist, we are going to see the commonly asked, right, data structure type implementation, system design entry questions. These kind of questions are very common, right? And I think this LRU, Cache, LFU, these two, three things are right favorites. So whenever there is some OOPS question and whenever there is coding, right, coding round for the system design question, they ask us to write either pick some famous company design architecture, then ask us to implement some OOPS implementation of any one functionality. So, and these are also one of the common questions like LRU cache, then we have LFU, then sometimes they ask for the tree implementation, sometimes they ask us to write pick a functionality from Uber, just say book a ride and write this OOPS code for it. So commonly interviewers, right, generally prefer if you do it in Java because this Java is one of the industry standard, right? Most of the companies use it, most of the big enterprise edition software run in Java, that's why. Okay. So let's see this question, that is LRU cache. So we'll discuss it in two parts, okay? First part is basically brute force, right? How can you brute force it, okay? When just no focus on time complexity, okay? No focus on time complexity. Second part will be optimization, okay? Get in of one and put in of one. So let me explain this question to you. LRU cache basically is least recently used. Least recently used, what does it mean? Let's say you have three items, okay? One, then two, and three, right? So this is some timestamp t equals to 0, right? This is t1, t2, t3, sorry, right, 4. You said some timestamp 4. This is 2 at timestamp 5, and this is at timestamp 6, you again 3. Now, tell me, at this point, right, at 1, so 1 is used currently, let's say. Now, if we are at 2, right, at point 2, see, timestamp 2, which one is least recently used? 1, right? Least recently used, मतलब सबसे पुराना कौन सा वाला? See, every cache, right? The memory of a cache is limited, right? Okay, so it's not like we can store infinite, right? No infinite storage, right? So there is a limit on how much items we can store. Let's say right now we have a limit of 2, just for this case. So even if you use some Redis cache or any cache, right? There is a, say, let's say 128 GB or something, that is limited, right? Okay, so now when you come at 3, right? Now you have two items, 1 and 2, right? When you come 3, you need to add it basically. Okay, 1, 2. Now when you add 3, you have to remove an item from it, right? Remove an item. Which one to remove? Least recently used. So which one is least recently used, right? This is used at timestamp 1. Say, let's say timestamp, right? And this is used at 2. So, right, this one is older, right? So we are going to remove it basically. So now what will it becomes? It becomes 2. It becomes 3. What is the timestamp? 3. Timestamp 2. Now when you come to 4, the same process repeats, right? So the same process repeats means what happens basically? You see, in your cache, now you're 2 and 3, right? Which one is the older one, right? 2, right? So you are going to evict it. So when you go, you put 3, you put 4, right? This is a time period what? 3. This is time period 4. Okay. Now when you come to this again 2, you again this one older, right? So 3, you will remove. So this becomes 4, this becomes 2. T equals to what? 5. T equals to what? 4. Now for the last one, okay. Just let me make it a little bit difficult. This is an easy example. Let me say it 4 again, right? Okay. Now if it's 4, then what happens? See, my 4 was there already present, but it was last used at t equals to 4. But now I again have 4. So what it will do? It becomes 2. It becomes 4, right? This is used at t equals to 6. This is 2 equals to 5. So if there is another one, right? There's a, let's say another 3 comes at timestamp 7. So what we are going to do? This one is older, right? Older. So we are going to remove it. So we are going to put, let's say this is 4, this is 3, this is a timestamp 7, and this is a timestamp 6. So this is what you have to implement basically. Okay. So now you should be able to answer the question, what is an LRU cache? Okay. So let me write it in a systematic manner so that I can post this whiteboard as well. So right now you should be able to answer, right? Now you should be able to answer what is LRU, right? Be able to answer what is LRU. Okay. Okay. Good now. Okay. Now LRU we need two functions basically, right? One is get, that is a key to check if a key is present in the what is in the cache or not, right? Then second was key and value, right? This is what then you have to put. Okay. Okay. This is what you have to put. Okay. Now see which is the best data structure to check if something is present, right? Something is present and it has a value in of one time basically. HashMap, and that is unordered one, right? Because HashMap, what happens? It's a key value pair, right? Key value pair, right? So can I check in O of one, right? If a key is present, right? Okay. Check if a key is present. What is the time complexity of this one? O of one. Okay. The next, right? Return if present. Return if present, or let's say access. Again, what is this O? One, right? Okay. Now, this is the easy part, right? We can easily get. Now tell me the put one. See, if you, if I ask, right, you have to put a key, right? There can be two cases, right? Case one, see it's already present, right? If it's already present, a key, what you are going to do? Update, right? Update and see what we did here, right? See, you see, there is a key 4. When we try to update it, we again put it at top, right? Okay, and mark it as recently used. Okay, right? Now, what is the other case? See, if it's not present at all, then what you are going to do, right? Add, right? So we basically add to our map basically, right? And again mark recently used, right? Okay, so these are the two functionalities that we need. So we have already seen, right? Get we can do in O of one. Okay. Now the problem is this put one. Okay. So let's take one brute force now. Okay. So let me write beside this, right? So this is not a brute force, just say a thought process. See which data structure is used, right? To pick the what do we say? Initially added something, right? If I add something, let's say A, then I post it B, then I post C, then I post D, right? Then something come again A, then some B, and so on, right? Which what can I use to do this? There are two things, right? Either I can use a queue, or can I use a less simple, right, array type, right? So let's say my, since we have a limited capacity, right? So let's say our capacity, right, equals to n basically now, right? So either I can have array, right, array of size n, or a queue of size n, right? Now tell me, see, uh, when do we see get is already sorted, right, in open. Now the problem is put, right? So how we are going to put it? Basically, what we need to check if a key is present. This we can check in via HashMap, right? Then we check in the map. Then we need to know, see, we need to know at which, right, where it is present, basically. See, if the key is present, if the key is present, at what timestamp? At what timestamp? And its position in cache, right? See, if we don't know its position, if we don't know the position, then how are we going to remove it? Why it's needed? Why? So that we can, right? So that we can remove it and add a recently used, right? Right? Okay. Now let's say what happens when I someone asks me to put a key and value. What, see, then in the hash map I can check if it's present or not, right? Say if present, this can be checked in O of one via hash map. Okay. Whatever its index, right? Then what we have to do? One first is say remove from our array or queue. Second is what? Add to the end, right? These two operation I need to do, right? Okay. So if I have this array, right? Let's say this is my array, some 2, 4, 2, 6, 7, right? And my key is 6. This is my key, right? So what do I do? I search, right? Right? I search it in of n basically, right? Because I have to loop over the entire, right? Either I have to loop over this entire array. Then what do? I remove it, right? Present. This way remove and shift rest of the element 1, right? So I'll do 2, 4, 2. So I'll do 7. This place is now empty, right? Shift right side elements. Okay. Now at the last position, now insert it again. Okay. Now this one is my least recently used, and this one is my most recently used. If I have some element, let's say some key equals to 3, you can see this is not present, right? Not present. Then what happens? See, then right, remove least recently used, right? So it becomes 4, 2, 7, 6, empty place, right? If we remove and what we are going to add a 3, right? Our new key, right? There was a 2, oh, right? Okay, we have it 2 multiple times, right? In cache, so just say 12 high. So you can put it 12. Okay. So if we take this approach, right, can we solve this question, right? So then what is the time complexity? Then get is solved in O of 1. What is done in O of n, right? And what data structure we used? What was our design for this one? Design for this one, there is a HashMap cache. Okay. There is a cache capacity we need. Okay. There is a one present, right? Let's say position, right? Let's say position array, right? Then what is there, right? Add, right? Add run in of 1, we have a add. Okay. Then we have a put we need, right? Inside this put, right? Put is of n. Okay. Of n. Then there is a search, and right, there is a search and shift of, this works in of n, right? What it does, search for a key position, right? It search for a key position, remove it, adds it to end basically, right? It search for a key, removes it and adds it to end basically. So this works in of n time complexity. So can I say this is my design now? Okay, good. So we solved basically one part, right? But this was brute force only. Okay. Now, now we need optimization. No, see, let me do a clear division. Okay. Now, what was the problem with your brute force, right? See, what was the problem with brute force? We have to search in OFN, right? We have to search for position basically, right? We have to search for position of OFN. So, which data structure? Now, answer this question. Which data structure, right? How to search, right? Search for a position in OFN and insert. There were two operations. Remember this thing: search and insert, right? When we write this algorithm, what did we write? We write search, shift, and insert, and the removes it and adds it to the end. You see this thing: search and shift and add it to the end basically. So this thing is important. Okay. Now this is what we are need to optimize because this put internally calls this one, right? Okay. Search for a position of an and insert. Okay. Insert, right? Insert and remove from there. Which data structure can do this in O of 1. Search is done by HashMap, right? This takes only O of 1. So search was search for a position, search and insert it and remove. This one was O of 1, right? This entire operation. Okay, now search we can do via HashMap in O of 1. Now we need to insert at end. Okay, insert and end in Q or something, right? We can insert in O of 1, but how to remove the element, right? Remove element in O of 1. Who does this? There's only one data structure, that is linked list, right? Correct. See, I have a node A, B, C, right? This is its next pointer. Say this is its previous pointer. This is its again next. This is previous. Can I, if I know this, right? If I know this position, right? See, if I know this position, can I do simply write this? Can I make this as next and this as previous? Can I simply do this? Then what happens, right? This my A connects C, C connects is what? A, right? And what I do C connects, I do B, I do B ka previous C. Can I do this simply, right? Can I do this? Yes. Because this is a linked list, right? We can always update the pointers, right? So this is a memory position, right? At this position, this simply means, right? This is a memory position, right? We can simply, right? We can point to it, right? We can point to it, right? We can do this, right? This is of course, right? Okay. So now let's see how we are going to use this. Okay. So now we have seen we have hash map, right? Hash map was needed to search in O of 1, right? Search. Second, insert and remove. This was done in O of 1 using what? Linked list, right? This is WY because it has both, right? Previous and next. So if it's previous is next, we say W linked list. Okay. Now, now let's see how we are going to do it. See. Okay, let's say, what do I say? No, but the important thing is, right? Important thing, right? We need position of, right? Position of, right? Position of pointer to each key, right? So if we need position of pointer to each key, where are we going to store it? Where will we store it? Say hash map. That's obvious, right? If we need to search and we need to know, we need to answer if it's present, which data structure is best? Of course, hash map. Okay, so now let's say this is my list node. So this is my node, right? So it contains my key, it contains my value, okay. Then it contains next and previous. These are both the list node type basically, right? Previous comma next pointer. Okay, now my hash map, right? Our hash map. So our hash map will contain what now? Our hash map will contain integer and this node basically. Okay. Now see, we have now a key comma list node pair basically. Now, can I tell position, right? Position of key in O of 1. Yes. Yes, I can tell the position in O of 1. Okay. Now, okay, let's see one example. Okay. Let's see, we have 2, right? Then we have 5. Then we have what? 3. Then we have again what? 5. Okay. And my capacity equals to 3, right? So I did 1. 2 I insert. Okay. So let's say 2, this is my 1 node, right? 2 node. So this is my map. So our map will contain 2. Let's say this position is some hash 10, hash 11, hash 12. These are some position, right? Memory pointer. See, this is not an actual value. I'm just writing for a reference so that it's easier to understand. Then I start 10. And what this 10 position of? This position contain my list that present my key, its value, its next. What was the next of it? We'll see, right? So initially, right, this is null, right? There is no, right? There's only one element, right? Okay. Now, when I insert 5, it got inserted at this position, right? 5. So I'll do, right, 5. Let's say this is some value 10. This is some value 15. This is some value 10. This is some value 3, right? Okay. Now, when I insert 5, what was its value? 5. See, what is its previous, right? This is previous. Okay, which is its previous? This 10, right? Hash 10, right? Its previous was null. Its next will be what? Hash 11 because this new value come. Now this is hash null. Okay. Now see, now comes the again 3 come. Right, when this 3 come, I am going to add 3. When I add this 3, I will update it with 12, right? This next pointer. What is its value? 10. Now what? See this. What is its previous? Hash 11. What is its next? Null because there is no next yet. Okay. See, this is key value previous next. Okay. Now again comes the 5. Now, so I'll insert in my map, right? My map will store 2 comma this, 3 comma 3, right? This position my map will store. So this, whatever I did, what I written is wrong. Okay. So map is going to, right? 2 corresponds to hash 10, then 3, right? Then come 5, right? 5 corresponds to hash 11, and then again 3 come, right? 3 corresponds to hash 12. Then I come again 5, right? I check if it's present, right? Present, yes. So what I'm going to do, see if it's present, right? See, then this was, let's say, see, right? This was my key, right? 2, 5, 3. This is next. This is previous. This is next. This is previous. Now, if my 5 come, right? First step is remove it, right? First step is remove it. Okay. Remove it. I know its position, right? Map of 5 of 11, right? This pointer equals to hash 11, right? This is by hash map. We know it, right? Okay. So if we know, then what I'm going to do? Whatever is previous of this one, right? So what is its previous, right? Can I know this via this thing, right? Has 11. What's its previous, right? 10. Okay, so my current node is what? So my current node is what? Has 11 position is what? 5, 15, 10, hash 12. This is previous. This is next. Now, if I want to remove this one, then what I'm going to do? So I will do this previous, right? This previous. This one, right? Hash 10, this one. So it's next, right? This, right? This is pointing to this one, right? Now if we remove, then this, right, this will point to this one now, right? Okay, so what we are going to do, we are going to change this one, right? So we are going to change, right, hashtag what? Previous 10 dot next equals to what? So it's next equals to what we are going to do now? 12, right? Whatever the next of this 5. Okay, and whatever is the previous, right, what we are going to do? 10, right? See this previous, right? We will update it to come to this one, right? Then this is removed now, right? Now this is removed, right? This is removed. So when we did this, what happened to my new list now? So hashtag 10. This is, let's say, my memory pointers. Now this is removed. So what happened now? 2, 10. Its previous is null. And what is its next now? 12, right? You see this one? Okay. This one we removed. And what is this one? This one is what? 3. And what was it? 3, 10. Its previous we changed to 10 and its next points to null. Now, right? Now step 2, right? Reinsert it, right? Now we are going to reinsert it at the end. If we have to reinsert at the end, right? I will just update this position here. So hashtag 11 because I am going to point this one, right? This is now going to point to 10. So 5, we are going to update the value. 3, this is what? Update value, right? Okay. Now, where its previous points to now 12, right? This is my, this is previous, right? I am going to add this 5 right here. So this becomes my previous and this next, right? These two things I need to update. Okay. Then where this next, right? This next now, okay, previous points to 1, this points to now 11, right? This one is next now. Okay. And where its next points to null. Okay. So now you have seen, right? Reinserted it. So to reinsert, what we did, right? So we did our tail, whatever our tail, right? Okay. See. So let's say our node, right? See, this is our node, and then we have one tail. So when I did what I did, see, this is my earlier tail, right? So earlier tail of previous, right? Earlier tail of previous. See, tail of previous, that will still remains the same, but now this will become my new tail. Okay. So what am I going to do? This node, right? This node of previous equals to what? Tail, and tail dot next equals to what? Node now. Tail equals to what? Tail dot next. See, this is updated, right? Reinserted and okay. So if we did this, all of our operations take off one time, right? Okay. So therefore, can I say time complexity is now of 1 for what? Remove and reinsert a tail. Okay. See, this is done now, right? This is what we need. The optimized solution now. So if you want to see the final design is what? Okay, final design. Final design is what? We have a hash map of what, right? We have an integer, we have a list node, right? Okay. This is going to be your cache, right? Okay. Then one we have is capacity, right? After from capacity, we have two things, right? Uh, Head, comma tail, right? Okay, let me write them clearly. So we are going to write list node. We are going to have head and we are going to have tail, right? Okay. So once we have, then one method we need is add method. So add method does what? It adds a key basically, right? So what do we first check, right? So what we are going to do? So it was get, right? There's no add. Get. Get what does, right? Remove key, insert a tail, whatever this node, right? This function will take node, right? Right? Current node. And this is also will say node. A node equals to, right? Cache dot getter key. Okay. Then next one was put. Put also as case, right? What does put does basically, right? If it's present, what's it going to do? Update it, right? Update, remove, then what is going to do? Insert it, tail, else what's it going to do? If present, if not present, then what's it going to do, right? Add to tail, right? Then if our size greater than capacity, right? Remove head, or let's say remove. So this was the entire code, right? So now what is the time complexity of these one, right? Then two methods that we build, right? First is remove a node. Okay, next one was what? We had, right? Insert a tail basically, right? So what is this time complexity of this one? O of 1. Time complexity of this one, O of 1. Time complexity of this one, O of 1. Time complexity of this one, O of 1, right? Yeah, that's it. So now let's see the code part. So you understood it, right? How we reached from this. See, earlier the only problem with what we had with the brute force is that we need to search, shift, and remove three things. right? Search, shift, and remove. That was initially done in O of 1. That we need to optimize, and to optimize this, which data structure is best that can do, right? That can remove and basically, right, update it in O of 1. That is linked list, right? That's why we are going to use the linked list here. Okay, let's well see the code part as well, right? Thank you. Okay, so let's see the code part for this one. I solved it base pair though. So what do we need? So let's start with basically what we needed. We need in the code we checked, right? We need method to remove. We need insert a tail. We said, right, we are going to use the linked list, doubly linked list, right? Doubly linked list. Okay, so we are going to define that, right? Can I say just node, right? Node contains values, right? It contains my key, right? Then it contains, right, to next and previous pointer basically. And what is the default constructor? Int key, int value, right? What it's going to do, right? This dot key, this dot value, right? Okay. Now inside this LRU cache, what do we needed? We needed a hash map basically, right? Hash map of what? Integer, comma what? Node, right? This is our cache basically. Cache equals to what? New. This is our cache. Okay. If we have the cache, then we need the capacity as well, right? Then what else we need? What else we need? We need to head pointer, right? So node, we need head, we need tail. I think this is fine. Now once LRU cache, then we need to initialize this. Right? This dot cap equals to what? Capacity, right? And init head tail, right? So what do we do, right? Head equals to, can I say new node? So this is initially, right, some let's say fillers or say something, right? Minus one. Now I have head and tail, right? These will be, see, this will be my head. There will be some element, there will be some tails. This will be like this, right? This is going to be a list. Let's say double A linked list. Okay. This looks good. Now, when we do get, okay, so when we do get, what do we write? We are going to check, right? If cache dot contains, right? Key. See, key. If it contains key, right? Other, if it don't contain, we are going to return -1. If it contains key, we are going to return what, right? If it contains key, right? Node current equals to what, right? Cache dot get what, key, and the value will be current dot value, right? But see, now it's recently used, right? So what do we have to do? Remove inserted tail. Okay, so we'll call remove our current node, and then we are going to do insert, right? Insert a tail. So when we insert a tail, what we have to insert? Current we have to insert at the tail. Okay, so we need these two methods, right? So it's a private, right? Private void remove node current. See, if I have to remove the current, then what I'm going to do? See, current dot previous, right? Whatever's previous of current, its next is going to what? Current dot next, right? Okay, now next thing is current dot next dot previous equals to what? Current dot previous. See, previous next is we are going to skip this one, right? And whatever's the next, whatever's the previous of next is what's the previous of current. Okay, now one next method we need it private insert at tail, right? This is also void type, and what do we have to do? We have to insert the node basically, right? So we have to insert, right? We are going to insert, right? Our linked list look like something like this tail, right? So tail is our basically end. So what happens, right? Tail dot previous dot next equals to what? Current, right? Tail dot previous, right? That is this node, right? This node, and we are going to this, right? Head A C. This is what we are going to do, right? So tail previous next is this one. Okay, now current dot previous, right? Tail dot previous, right? Now current dot next is what? Uh, tail, right? Is this correct, right? We did tail. See this. We need this A dot previous, right? This is our A. A dot next we need current. Okay. Now tail dot previous, right? This tail dot previous. So we haven't updated, right? Tail dot previous will be current. Tail dot previous, right? Now tail dot previous is current. Okay. Current dot next is tail. Current dot previous is A, right? That is tail dot previous. Looks good to me. Or this too much things. Uh, okay. This is fine. This is fine. Now we have to put it right. If we already have the key, right? If cache dot contains key, then what we are going to do is just update, right? So what we are going to note current equals to what? Cache dot get key, right? We get it. Then what do we do? After getting it, we are going to let's say remove, right? Remove current. We are going to insert a tail current. Then current dot value, right? We are going to update its value, right? This is correct, right? Okay. If this is correct, if it's not present, right? Not present. First is right. Node current equals to what? New node. Key is what? Key, comma. This is our new node now, right? We need to insert a tail. So we need to insert this at tail. We inserted this at tail. Okay. Now what do we have to do? Move head basically, right? So head dot next is what? Head dot next, and head dot next dot. See. So this is something like this: head A B, something tail, right? We did head A B C tail, right? But we need to remove this A. So what are we going? Head dot next is what? Head dot next, right? Okay. Then but this previous, right? Previous of this one, head dot next dot previous, right? This is going to be head. See, head dot next what we did? This one. Okay, this one is here, right? Head dot next dot previous. Now we did head, right? And when we remove this, right? So we remove head, right? If right cache dot size, right, greater than capacity, then we are going to this, right? We don't have to return anything, right? Okay. I mean looks good, but let's see. See, they said tail dot cannot assign field next because tail dot previous is null. See, this is tail, right? Tail dot. Did I remove it early? Then first let's say insert, right? Let's insert first, then remove. I don't know, right? If I maybe it happened, right? I removed it, then I inserted. No. See current, right? See current dot previous is what? Tail dot previous. Current dot next is what? Tail. I think this is unnecessary. See this is current I. So current dot previous. This one, right? Here's some mistake. Did we forward something? See we updated this value here, right? Okay. Current dot value we did. So it was suppose I am returning -1, but should be present. Okay, if we have to insert a tail, to insert a node at tail, we are inserting it, right? I think I haven't inserted this at cache, right? Cache dot put, right? Key current, that also, right? We need to add it to the hash map. Okay, no. See, head. This is my current node, right? Maybe I'm complicating, right? Current dot next equals to head dot next, right? Current dot previous equals to what? Head. As over complicating, right? This current I insert. No, this is wrong, right? So head inside current head equals to head dot next, and we need to remove this thing basically. So I'll say, right, head dot next equals to, right, current head dot next basically, right? And current head dot next dot previous equals to head. This is the same thing, huh? What is the difference does it make? Hmm. We have to remove it. Are we missing something? Figure it out. This seems correct. We did, right. Oh, okay. Head dot next is what? Tail. tail dot previous is what? Head. Silly. Okay. Cannot assign previous because next is no. Still some method is wrong. Let's change this. No, let's use that remove method here, right? We need to remove the head dot next basically, and we also need to remove it from cache, right? Cache dot remove, right? Head dot next dot key. So now it should work. Cannot assign because some method is still wrong. Is this right? Because this seems correct. I think that one was correct, right? Tell dot previous dot next equals to correct, right? We need right. Still we are getting some error. So I removed it, right? Okay. I inserted it at tell and I updated the value, right? Okay. Node current equals to new node. Let's see this example where it is getting wrong. So we inserted initially, we initialize this dot capacity, okay. Now what happens? The first is put, right? Put 1, put 2, 2. Now when it does get 1, we insert at tell, we when I insert at tell, am I not updating the position in, right? Remove current, right? Now what we need to we need to update this new position in hash map, I think, right? Hash dot put, right? What key is what? Tell dot previous prev because it's new position now. We still have something wrong. Okay, I remove it, I insert it at tell, then I update it, right? No, do we need to update, right? We don't need to update. I think I was inserting and then I was removing. That was we have to remove and then we have to insert it there. Please work. Finally. This linked list is not this pointers is not good, but yeah, this is the approach, right? You understood the approach, right? Okay, let me know in comments if you have any doubts or anything.